Welcome to the DSA series. In case you're wondering what you're doing here, I'm sure you're interested in DSA, data structure and algorithms, which is why I've stumbled upon this video. In case you're wondering who I am, my name is Kallol Bhattacharya and I have been in the IT industry for the past 24 years, recently retired. And I thought that my knowledge in the IT industry is best put to use if I am with you and I'm trying to impart whatever I have learned in terms of these lecture series. DSA, Data Structure and Algorithm, is going to be an exciting series, and we will cover everything from the basics of DSA to the advanced concepts of DSA. We will cover a plethora of questions that are typically asked in the university curriculum. So anybody who is interested in DSA as a topic, as a subject, anybody who has DSA in their university curriculums, they can definitely benefit out of this. Be with me. I'm sure this is going to be an exciting journey in order to prove how and what modern algorithms can do. Thank you so much. Hello. Welcome back. Good afternoon, good evening, good morning, depending on whenever you're watching this. We are back with one of the key elements of DSA, which is asymptotic notations. And we'll try to cover in this lecture what is the necessity of asymptotic notations and why do we need to actually understand asymptotic notations. For now, on the screen, what you see is what we have covered as a part of our module 1 exercise that we were trying to cover. All the previous lectures are available for the yellow font items in the playlist. Please feel free to visit that. Before coming into asymptotic notations, it will be useful for you to understand that. On the asymptotic notations is what we will try to cover in this lecture, and a subsequent lecture will be there to cover linear search and binary search techniques and their complexity analysis, which would complete our module 1, and then we can move on to the rest of the modules that we intend to cover as a part of our DSA course and curriculum. Now, what do we cover today? We cover asymptotic notations, as I said, and what is it, why do we need it, all of that we'll try to cover at length. Typically, we will cover 3 notations, which is a part of any university curriculum, any university syllabus, which is big O, omega, theta. And why do we use it? We'll cover some examples across big O, omega, theta, how to calculate it, when to calculate it, and what are the tips and traps in order to be careful while calculating it. And of course, because we will be completing asymptotic notations, we will now attempt to solve typical university questions that come as a part of asymptotic notations. Now, that being said, let us deep dive into asymptotic notations. What you see on the screen is what we have already covered in the last lecture, where we talked about the time complexities and the various time complexity classes that we can represent on the graph. What you see on the graph are the time complexity classes, well-known time complexity classes. For example, the constant time complexity class is represented by order of 1. Logarithmic is represented as order of log n. Linear is represented as order of n. Log linear is represented as n log n. Quadratic, yes, n square. Exponential 2 to the power n. In between quadratic and exponential, you would have any kind of polynomial, which is n cube, n4, etc., etc. And after that, you have a worst case polynomial or worst case class, complexity class, which is order of n. Now, what are these classes? We discussed it briefly in the last lecture. We will deep dive now into these classes. When given a particular polynomial as something that comes out of your time calculation or time complexity calculations of your algorithm, you would be forced to probably find out whether this particular time calculation that came fits into any one of these classes, right? So it has to fit into any one of these classes, right? And then you can actually go to the external entity, whoever you want to proclaim that, yes, I have created an algorithm which is of constant time, which is of logarithmic time, which is of linear time, right? So if you see this 6, if you calculate for any algorithm and you get a time complexity of 6 from that algorithm, and please refer to my previous lectures how to calculate it, you will understand. Now, I'm not going to go there. I'm just trying to jump into the deep dive of the complexity classes, and that's where I'm trying to explain that if you get a time complexity of 6, it means that you can directly jump into this graph and say that I have designed an algorithm which has a constant time complexity, and it does not vary with the number of inputs. If your time calculation for your algorithm becomes 3n plus 6, right, of course it depends on n in a linear manner. So you can directly say that my time complexity of my algorithm falls under the complexity class of order of n, which is a linear complexity class. So what is it helping? For example, this particular time complexity, it is a quadratic time complexity, and I can immediately go and say that my algorithm that I have defined is falling under the quadratic time complexity graph. Now what it helps is for people to understand who don't know your algorithm that you have defined something which grows with n in this manner, or which grows with n in this manner if it is linear, or which grows with n in this manner if it is completely independent of the inputs. So what are you defining? You are defining a method to tell people what kind of algorithm you have produced, whether you have produced a linear class of algorithms, constant class of algorithms, logarithmic class of algorithms, and that you can clearly say from what you see here, right? So if it is not having n, it's constant. If it is having n, check the highest power of n. The highest power of n will tell you which class it will fall under. Highest power of n here is 1, so it falls under the linear complexity class. Highest power of n is 2, it falls under the quadratic complexity class, and so on and so forth. But suppose you have from your algorithm an expression that comes out like this, which is the time taken by your algorithm. So if you calculate the time taken by your algorithm for a particular algorithm, let us assume that the time taken by that algorithm has come to be like this. Of course, it depends on n. We can see that. Now, how will you tell somebody which complexity class this will fall under? You cannot, because neither it falls here, 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 and these are well-known complexity classes. We are talking well-known complexity classes beyond which there are very few complexity classes which people know, right? So these are the complexity classes that people know, and they can correlate your algorithm to that complexity class and hence can judge the algorithm. But now you are in a soup. You don't know what complexity class this will be, right? So if you don't know what complexity class this will be, how do you tell people as to what could be the maximum time your algorithm can take? What could be a probabilistic minimal time that your algorithm can take? What could be a probabilistic average time that your algorithm can take? Right? So that is where we struggle. So for example, for this, we can immediately go and say our algorithm will take quadratic amount of time, and everybody else will understand. And you are also very, it's very easy for you to probably find out that this will take quadratic amount of time. And you will rely on the time complexity classes to inform the whole wide world that I have designed an algorithm which takes quadratic amount of time. But you cannot say for this that it will fall under which complexity class, right? It can fall under any complexity class, or it may not fall under any complexity class at all. It might be somewhere in between. So if you carefully see this expression, and we will not go there, it's beyond the scope of this lecture and beyond the scope of your syllabus, that the complexity class, if you draw the graph of this with respect to n, you will see that you are actually drawing a graph like this. So this is your Tn, which represents the left hand side, whatever we see here. This is what is represented on the right as a complexity curve of the time complexity that we see on the left. It will be between linear and logarithmic. And the point that I'm trying to make is you do not have any complexity class in between to tell people that I have designed an algorithm that is XYZ. You cannot say it is linear. You cannot say it is logarithmic. And because it is in between and it doesn't have any name given to the complexity class in between, you cannot say what name it actually adheres to. So what do you do now? How do you make people to understand that you have designed something and this is the complexity that it might exhibit? Because you cannot marry this particular Tn, the complex Tn, if we call this as a complex Tn, right? And if we call this as simple Tns, right? Simple Tns were good. They were marrying to one or the other complexity class, right? But complex Tn is not aligning to any complexity class. and it is somewhere in between. So what do you do now? How do you tell people that I have defined an algorithm, designed an algorithm, and the complexity class is this? You cannot. Right? That is where asymptotic notations come into existence. They will define that while yes, you cannot say what complexity class they fall under, but at least you can say that the complexity of your code will not exceed the linear class, and the complexity of your code will not go below the logarithmic class. So what you just now defined is the big O notation to identify the upper bound of your algorithm, and omega to identify the lower bound of your algorithm. Again, I'll repeat, because your TN does not have a conventional complexity class, and it is a complex TN, and it doesn't have a conventional complexity class, you cannot tell people that this is my algorithm, this is the amount of time it might take, etc., etc. Hence, big O and omega will help you to tell them what is the upper bound of your algorithm and what is the lower bound of your algorithm. The upper bound of your algorithm will be the upper known complexity class above Tn, and the lower bound of the algorithm will be the lower known complexity class below Tn. And then you can go and say that my algorithm, which is Tn, which is this, does not take more time than a linear class, which is order of n, because my upper bound is order of n. And you can tell them that my Tn algorithm does not take any less time as a logarithmic complexity class, which is order of log n, because your lower bound is order of log n. So the lower bound is expressed by the big O notation, the asymptotic notation as omega, and the upper bound is represented by the asymptotic notation big O. And in case if we could have found the actual time complexity of Tn, or the average time complexity of this graph, right, then we could have actually established a time complexity which we would have called as theta, which is called as the average time complexity. So if we summarize, we have just now understood that big O refers to the upper bound of an algorithm, omega refers to the lower bound of an algorithm, and theta refers to the tight bound or average bound of an algorithm. And what do these help us in? These help us in case our complexity, our time calculated is complex in nature, then I cannot represent my Tn as a standard complexity class. So there will be a big O which will be defining the upper bound of my algorithm, and there will be an omega which will be defining the lower bound of an algorithm, of my algorithm, so that others can know what is the maximum and minimum amount of time that they can expect out of my algorithm. And in case I can find out the average case of my algorithm, that will be represented as theta, which is also called as the tight bound or the average bound of the algorithm. So that is the need for asymptotic notations. If we would have understood what I'm trying to explain, and I hope you can appreciate the fact that big O, omega, theta are not best case, worst case, or average case. They are not required, or they are not used to represent best case, worst case, average case. There are many people who would probably think otherwise, but if you think deeply, it's not that. It is just a notation. It is a notation to signify your upper bound. It is a notation to signify your lower bound of what? Of a function, right? Now let's say if this function itself is a worst case calculation. Let's assume this function is a worst case calculation, right? It includes the worst case of an algorithm, and hence the calculation has come like this. Now you are asking somebody, or you are asking the big O notation or the asymptotic notation to give you the asymptotic notation of this. Then you will get the asymptotic notation of this always as big O of n square, omega of n square, and theta of n square. Right? So what you have done, you are defining the upper bound of the worst case line. Right? So if n square is here, this is your n square. So you know that 4n square is what is defining my algorithm. Right? So 4n square for 5n plus 2 means that you have a time complexity of order of n square. Now that particular polynomial is already a worst case, because it takes into account the worst case scenarios, and hence you had calculated this polynomial like this. And because you calculated the polynomial using worst case, now this line represents a worst case line of your polynomial. Right? If this line represents a worst case line of your polynomial, then the upper bound of this particular line can be order of n cube. Yes, I understand. It can be logarithmic n log n. Yes, this can also be the lower bound of the worst case possibility that is here. So the problem is that because this is a well-defined complexity class, right? And we know that order of n square is a well-defined complexity class. And as I established that this is your worst case complexity because it is arrived from the worst case polynomial. So the worst case polynomial says that my worst case complexity is order of n square. So the worst case polynomial, if it is plotted on this curve, then the upper bound of this polynomial will also be order of n square, because you have to take the nearest upper bound of a class which is very well known. The nearest upper bound of order of n square is n square itself, and nearest upper bound of order of n square, nearest lower bound of order of n square is also n square. So basically your upper bound is n square, your lower bound is n square, and your average or tight bound is also n square, which is why you write order of n square, omega of n square, theta of n square, because all of these represent worst case upper bound, worst case lower bound, worst case average bound. So I hope you understand that worst case is not represented by a lower bound or an upper bound, and best case is also not represented by a lower bound or upper bound. Upper bound and lower bound are for this polynomial. This polynomial itself has inherently the behavior of being a worst case or being the best case, and that means that it will always have a line. This polynomial will always have a line. So if this line is matching with a best fit or a conventional complexity class, then you will have upper bound the same, lower bound the same, and theta also the same, that is average bound. If it doesn't, then you will have a different upper bound, different lower bound, different theta, which is perfectly fine. Like for example, this complexity class did not match with anything. So this, whatever it represented, had an upper bound of on, had a lower bound of o log n, which is fine. So the upper bound would have been represented as o, the lower bound would have been represented as omega, and theta would have been the tight bound of this algorithm. But it has nothing to do with best case and worst case, because this line itself carries, this particular equation itself carries whether it is a best case, whether it is a worst case, or whether it is an average case. And accordingly, we create the upper bound on this and the lower bound on this, the upper bound on this, the lower bound on this, the upper bound on this, the lower bound on this, depending on whether it is a worst case or a best case or an average case. For the particular asymptotic notation, every polynomial is a line. The polynomial may represent a best case, the polynomial may represent a worst case, the polynomial may represent an average case, but it is a line. If it is a line, it will have a top line and a bottom line below it. If it is a line which is matching with a class, conventional class of complexity, the top line will coincide with the polynomial line. If it is a class which is, if it is a polynomial which doesn't match with the class, the top line will not coincide with the polynomial line. And similarly, the bottom line will not coincide with the polynomial line. Right? So what are we saying? Polynomial line is worst case, best case, average case. And on top of this line, because it is just a line, you can draw two more lines, which is the upper bound and lower bound. Sometimes these two more lines will coincide with the main line, polynomial line. In case the polynomial line is a well-known complexity class, the upper line, lower line will coincide. So that becomes your upper bound, lower bound, average bound. Of what? Of probably a worst case polynomial, of probably a best case polynomial, of probably an average case polynomial. So please remember that upper bound, lower bound, average bound is not best case, worst case, or average case. I hope I have made this particular point, which is a very sensitive point, because there are many people who would phrase these in their own terms, in terms of best case, average case. But yes, conventionally, if I say conventionally, it is a fact that people would call the upper bound as the best case. Sorry, upper bound as a worst case, lower bound as a best case, right? And the tight bound as something which is an average case, right? So my point here is that depends on the situation where you will have to imply, or where you will have to include the knowledge that whether you are going to represent the upper bound as the worst case scenario, whether you are going to represent the lower bound as a best case scenario. Sometimes in your university papers, you would see they are asking for best case, average case, worst case. If they give you a polynomial, then the best case, average case, worst case will be basis that polynomial's line. And I'll teach you how to do that in this particular lecture. But if they don't give you a polynomial and they ask you to do best case, average case, worst case, you'll have to see the algorithm and create those best case, average case, worst case. And those algorithms that you will see and then refer and depict what is your best case, etc., etc., that can be represented using the notations big O, omega, and theta, depending on what case you are actually solving. So now let's deep dive into big O notation. Now, what is big O and how do we actually justify big O? Now, big O, as I said, is used to classify upper bound, right? For any function, if this function is what comes out of my algorithm in terms of time complexity, so this is my time taken for my algorithm, 10 to the power 3 n square, then this line represents my algorithm's line as we move forward with n. Then I should have some line above me. I should have some line above me, which is going to be my upper bound. That means that if you see this, it says that if you have a function which is a complex function, let us assume this is a complex function, then we will have a function which is a simpler function. So probably this will be aligned to some conventional complexity class. This will have some complexity which is aligned to some complexity class. For example, here we can see n cube. So it is aligned to the n cube complexity class. So it's a simple function. Let us assume this is a complicated function. I know you can align it to n square, but let us assume this is a complicated function and you cannot align it to any complexity class. In such cases, can you define the simple complexity algorithm or simple complexity function along with a constant such that after a particular value of n, which is n naught, the c dot gn will always be greater than your actual function. So you had started with this complex function and you could not describe this complex function to the outside world, saying my algorithm is going to do this kind of a time complexity. So you said that I'm going to do a time complexity judgment in terms of my upper bound. So what is my upper bound? Can I find a simple function gn which is going to marry to a conventional complexity class? In this case, it is n cube. And can I put a constant so that this particular complexity class after some point of n will cross my fn? And if that happens, then this gn becomes the order of this fn. That is, this gn becomes the big O of this fn, which means that this gn is now the upper bound of this particular fn. So that's what it says, that fn will be equal to the order of gn or big O of gn if we can prove that for a particular value of n, my cgn will cross fn always. Cgn will be above fn. Cgn being above fn means that it is the upper bound. Upper bound for a particular, after a particular value of n. it will be a line which will always stay ahead of my Fn. And Fn, I cannot proclaim to the world that Fn is of this complexity class because it is complex. So I will rely on an upper bound which is conventional, and I will tell that upper bound to the world that my algorithm's upper bound is n cube. So I will say that it is going to be big O of n cube. How do you do it? Let us see. So now let us put our Fn, which is basically 10 to the power 3 n square, and our c dot gn is 1 dot n cube. Now let us look at case 1. Let us put n as 100. So then this becomes 10 to the power 3 into 100, which is 10 square into square. Because you have n square, that is what it is. So this becomes 10 to the power 7. If I take cgn, c is 1 and my n is 100, which is 10 square, a cube of that, which translates to 10 to the power 6. Now I have to prove, as per the definition of big O, that can I define a curve c dot gn which is above Fn? C dot gn above Fn means what? Please see here. C dot Fn has to be above gn. So I have to prove that c dot gn is going to be above my Fn. What did I get? I got c dot gn as below my Fn. So Fn is still higher than my c dot gn. So we are probably here on the graph where Fn is higher than this blue line, which is my c dot gn. Now if I take that n as 10 to the power 3, then I have 10 to the power 3 multiplied by 10 to the power 3 whole square. Right? So I have 10 to the power 3 already there, and then I'll multiply 10 to the power 3 whole square. So what I get is 10 to the power 9. If I am here, then I will get 10 to the power 3 whole cube, which also is incidentally 10 to the power 9. So we have an equal to here. So this is basically what we call as the inflection point. This is the point where your n0 is become at this value of n0, which is 10 to the power 3, you have the line touching, the blue line is touching the yellow line, which means your c dot gn is actually trying to cross Fn. And if we go one step ahead, we will see that it crosses. So let us take n as 1001. So we have Fn as 10 to the power 3 into 1001 into 1001. And in the other side, we have 1001 into 1001 into 1001, because we have n cube. So we can say that these will cancel out, and the only thing that remains on the right hand side is 1001, and the left hand side has 1000. So 1001 is greater than 1000. Right? So at n equal to 1000 it becomes equal, and at n equal to 1001 the blue line will cross. And what is the blue line? C dot gn. C dot gn will cross Fn at that value of n, which is 1001. So we are not interested when we don't have a way to tell our complexity. We are not interested in smaller values of n. We are interested in values of n which are large, so that from that large point onwards we can tell to anybody that our complexity, our algorithm's complexity, we do not know, but at least what we know is that the upper bound of this is going to be this and the lower bound is going to be this. We are talking now upper bound because we are talking big O. So what do we tell? What happened with this? Why did we do all of this? We found out that there is an equation. There is an equation called c dot gn which satisfies this at a value of n equal to 1001. So if it satisfies this at a value of n equal to 1001, then we can definitely say this. That is, my Fn is equal to order of Gn. Now what is Gn? If you see, your C dot Gn was this. If C dot Gn is this, and then C is 1 and Gn is n cube. So I can easily say this is my Gn. So can I therefore say my Fn is equal to order of n cube? So what did we achieve? We are now saying that this is going to be the upper bound of the complex function, which we could not tell the complexity about. We can go ahead and tell this to the world that my upper bound of my function is n cube. Whatever that function is, that function may be the worst case scenario function, it can be the best case scenario function, it can be the average case scenario function, as I mentioned earlier. But you can say that whatever that function is, I cannot say what class of complexity it aligns with. Hence, I will say I have an upper bound which is represented by this big O notation. So this is what is big O. It is represented by the big O notation as being the upper bound of this function. So that is on the big O notation. Now, if I go forward and we go into one more example of this, then let us say that our Fn, is 5n plus 5. Again, let us assume this is a complex function. We do not know. While we know it is linear, I'm saying forget about the fact that it is linear. I'm saying think about the fact that it is complex and you cannot tell what class it falls under. If you cannot tell what class it falls under, then you are supposed to say something to the people who are judging your algorithm. So you will want to say the upper bound of this algorithm. So to calculate the upper bound, what do? So you say Fn is equal to 5n plus 5. So you will have to find out on the CGN front, right? We are talking about CGN being 6.n, that is C is 6 and Gn is equal to n, right? And we are supposed to find a value of n when this will happen. When this will happen, right? Where CGN will cross the Fn. When that happens, it becomes the upper bound of your function. So what will happen here? If I say that case 1, n equal to 1, c equal to 6, then 5n plus 5 will become 5 plus 5, which is equal to 10. And if I say n here, then this is 6 on the CGN front, and this is greater. But I have to prove some value of n where it will be less. So let us go on. Let us go on and put n equal to 5. 5 5s are 25, plus 5 is 30. Now on the right side we get 6 into 5, which is 30. Right? So if I get this, then we can say that they are now equal. So we are now at that inflection point. At the inflection point where your CGN is trying to cross Fn. Now, if we go ahead further, one more step further, then n equal to 6 would mean this is 35, and on the right we will have 36. And you can see now that this has crossed, CGN has now crossed Fn. So since CGN has crossed Fn, we can say now that at n equal to 6 or after n equal to 5, whatever way you choose, you can say greater than 5, or you can say greater than equal to 6, whatever you choose, you can say that, and we can say therefore that now we have the upper bound defined by this particular CGN, which is 6.n. So what is my Gn here? C is 6, Gn is n. So my Gn is actually n, and it satisfies this particular thing. So this satisfies this particular thing, right? So if this satisfies, then this holds true. So if this holds true, then I can say my Fn is equal to big O of Gn. That is my upper bound. So what is the upper bound going to translate to? Gn is n, so upper bound is n. So do you now see that your function originally had a time complexity which was assumed to be complex? I said let's assume it to be complex. We cannot find out the time complexity. Let's assume that. Right, and accordingly I explained upper bound to you. Now if you come back to the fact that your time complexity is n, of course this time complexity is n, right? Do you see and appreciate the fact that your time complexity, the upper bound of the time complexity is coming to be order of n. That means your own time complexity is your upper bound. And I told you this, that if your complexity is a conventional complexity class, then your upper bound will coincide with your conventional complexity class. In this case, 5n plus 5 was a linear complexity class, so the upper bound came as the linear complexity class. Right? So if you see on the bottom part of the screen, and this is very important, if you see on the bottom part of the screen, these are your conventional complexity classes arranged in order from the lowest to the highest. Now we are talking that our big O has come to this. Now can I say that I will have something which can exceed Fn, which is of the order of n cube? Can I say that? Let's say this graph is n cube graph. This graph represents the time complexity of n cube. It's a conventional time complexity. It's a simple time complexity. Now all I said was there has to be a simple time complexity that will cross the complex time complexity at some point of n, right? And then we can say that simple time complexity is the upper bound. So yes, n cube is the upper bound of this particular function also. N, as we calculated here, is the upper bound of this function. N log n will be the upper bound of this function. N square will also be the upper bound of this function, because n square will look like this. This is also the upper bound of this function. So everything on the right of the minimal complexity that you find is the upper bound. So I therefore can conclude that for everything on the right, there will be a fact that I can prove that Gn is, let's say, n log n. I can prove Gn is n square. I can prove Gn is 2 to the power n. Right? In the same manner, I can prove this. I proved 6n is greater than 5n plus 5 for a particular value of n. Similarly, I can prove n log n is greater than 5n plus 5 for a particular value of n. I can prove that easily. And I'll show you the next example where I'll prove, I think n square or n cube to be greater than the function, same function. We'll go there. But if I can say that all these are also the upper bounds, all these are also the GNs, then all these are also the upper bounds. Because if these GNs satisfy this equation, then every of those GN becomes the upper bound or big O of the function. So can I therefore write Fn is equal to big O of n? Of course I can write, because that's what it came. If I can write Fn equal to big O of n, I can also write Fn is equal to big O of n log n. I can also write Fn is equal to big O of n square. I can write anything that is above n as the big O, that is the upper bound of that particular function. But conventionally, we have to write the nearest complexity class. That is, we have to write only this, big O of n. Now let us move to the next part where I said that I will prove to you that while we have 5n plus 5's upper bound as proven as n from our previous example, we will now prove that n square is also the upper bound of this function. Then it will be clearer, much more clearer to you. So if I start from here, then my Fn is actually 5n plus 5, the same polynomial. But I have changed my Gn. I have said Cgn is actually equal to 1 dot n square. Now if I have done that with the value of n equal to 1, I have 10 here. And what do I have to prove? Let's not miss that. I have to prove this is Cgn is going to be greater. So with the value of 10, I get on the left side. On the right side, I will have, for n equal to 1, I will have 1. So this is greater. When I take n equal to 5, it is 5 5s are 25 plus 5, 30. On the right side, I get 5 square, which is 25. So this is still greater. When I take n equal to 6, this becomes 35. But this becomes 36 because we have 1n square. So did we achieve what we wanted. We wanted our CGN to cross our Fn, and that's what happened here. This is where it is happening. So where is it happening? Between N5 and N6 at some point. Because we don't see the equal to, we can't say at what point, but between N5 and N6. So it is very safe to say that at N greater than equal to 6, you will have that inflection. So this rule becomes true. This rule becomes true. If this rule becomes true, what is your Gn? Your Gn is N square. So if Gn is N square, you can definitely write that Fn is bounded at the top, which means Fn's big omega, that is the bounded at the top, is equal to Gn, which is equal to big omega of N square. And therefore we proved that this is also the upper bound of this function. This is also the upper bound of this function. We proved it in the earlier slide, and we are proving it now that N square is also the upper bound of the function. So what are we saying? We are saying that for a particular value of N, we can say that there exists a function which is called as Gn, and this Gn can be, if it starts with N, it can be anything above N in the complexity classes, where we can assure that for a particular value of this particular N, these lines will always stay above the function line, which is Fn line. So that is your upper bound, and this upper bound is represented by big O. Again, I will recap that this function may itself be a worst case. This function may itself be a best case. We don't know who produced this function. When we calculated this function, we probably took all the best case scenarios and we calculated it as 5n plus 5. Then we can say that this is my best case function. So the best case function having an upper bound means this is an upper bound of best case. We cannot, or we do not say this is the worst case. Just because it is the upper bound, it doesn't become the worst case. Best case, worst case are the lines, and the upper bound and lower bound are on top of or below of the lines. That's what I wanted to recap, because this is something everybody makes a mistake almost. So how do you calculate those C and GNs? In these examples, I had taken C and GNs as something. How do you calculate given a value of polynomial? How do you calculate? And this question almost always comes. You will be given a polynomial, you will be asked to create or you will be asked to find big O, omega, theta. How do you calculate that? Right? So to calculate the big O, omega, theta of a polynomial, the simplest way is, if you are given this function 5n plus 5, put 5n plus 5 on the left hand side. On the right hand side, you are searching for what? You are searching for C dot Gn. Specifically, you are searching for the value of C, you are searching for the value of Gn. Right? So that you can later say big O of Gn. Right? If you prove that for a particular value of N0, your C dot Gn is greater than equal to Fn, then you can definitely say that your big O of Gn is the result of the function. So what we'll do is, we will take 5n, because 5n is on the LHS, and this 5 also we will make it as 5n. So then it means that we will have to show that this 5n plus 5, and on the right side we have 10n. So for a particular value of n, if we take n as 1, 5n plus 5 becomes 10. 10n becomes 10, so this is equal. So this particular line or this particular operator gets satisfied. So we can say now that my Fn is equal to, or we can say less than equal to, C dot Gn. And what is my C? My C, if you see here, my C is 10, my Gn is n. So we have found out our C, we have found out our Gn, and we have satisfied this equation for a particular value of n, which means now we can write that Fn is upper bound by big O of Gn, which means this is big O of n. So this is how you will calculate, given a polynomial, you will calculate the big O of that polynomial, right? You'll have to figure out what is your Cn, Gn, and then you'll have to substitute the Gn as the big O of that particular function. So you calculated this, right? So we had calculated this earlier, but the same polynomial function, there are several ways to calculate whether it's basically fitting to the upper bound, lower bound, average bound. We are calculating it like this. Now what we have, in fact, the last time we calculated it through taking trial and error. We took n square, we took let's say 6n, we took trial and error with case 1, case 2, and we found out a value of n. Here we are showing a generic rule to actually calculate big O. Now remember this, if this is possible, then this is also possible, because as I said, anything to the right of this is a big O, is an upper bound. So can we prove this? Let us see. So we have 5n plus 5. Now if you want to prove this as n square, because you already know this is n, then just make the right side as 5n square plus 5n square. So you have 5n plus 5 and you have 10n square. Put n equal to 1. As soon as you do that, this becomes 10 and this becomes equal to, because we have 10 on the right side also. So what did you satisfy? You satisfied that Fn is less than equal to C dot Gn. And what is your C? Remember this, we have this 10n square, so C is 10, Gn is n square. So what can you write therefore? That Fn is equal to big O of Gn, which means Fn is equal to big O of n square. So now you have again proved this, that the upper bound of the same Fn, which was found to be n here, right, becomes n square here. And we can similarly prove 2n, n to the power n likewise. So that the essence that we are trying to prove is, if you get an upper bound, any complexity class above those upper bounds are also the upper bounds, but you have to choose the nearest upper bound. So that being said, this big O part is done. We will move to omega now. I hope you have understood big O. Omega is basically the lower bound, so we have to just flip the story and it will be easier for you to understand now. So now we are saying that our CGN should actually be below our function to represent a lower bound of that function, right? So that is what we will try to do for a particular value of n. So it will become the lower bound of that particular function for a particular value of n. So again, we will assume that this is a complex function for which it doesn't match to any of the complexity classes. Hence, we have to tell the world that we have defined an algorithm. How do we tell the world what is the complexity of the algorithm? So we'll say we don't know the complexity. We know that the lower bound is going to be omega of this. That is what we will say, right? And to help us for that, we have this omega notation, right? And that's what we are trying to find out. Can we find out something below Fn for a particular value of n? For a particular value of n? For a particular value of n, can we find out a CGN which will remain below this Fn always? Then you have your answer, as the Gn will be the complexity, right? So let us figure out this. So our equation now has changed. It has flipped to saying that Fn is now going to be greater than CGN, right? So let us see that. Let us see what is our Fn. Our Fn is 2 to the power n. Our Fn is 2 to the power n, and our CGN is 1 dot n cube. So for case 1, n equal to 2, c equal to 1. If n is equal to 2, then this becomes 2 to the power 2. And this becomes 2 to the power 3. So we have to prove, we do not want to miss this, we have to prove that Fn is greater than equal to, but this definitely is not greater than equal to, this is less than. We have to go further with n. So let us take n as 9. If we take n as 9, this becomes 2 to the power 9, which is evidently 512. And if we take c dot gn, 1 n cube, this is 9 cube. So 9 cube is 81 multiplied by 9, which is probably 729. Somewhere round about that is what will come. So this still is less. Now let us take n equal to 10. So 2 to the power 10. 2 to the power 10 is what? 1024. And c dot gn, that is n equal to 10, if I put, then this becomes 10 cube. Now 10 cube is nothing but 1000. Now we have 1024, that is 1024 greater than 1000. So can we say that between 9 and 10 there is a point where this inflection happens? It will be safe to say our n0 value is greater than equal to 10. Where the inflection happens, that is our CGN will fall below Fn and hence becomes the lower bound of the function. So what is our CGN? This is the CGN. If this is the CGN, what is Gn? N cube. So now we have satisfied this equation. As you see here, we have satisfied this equation for a particular value of n. Therefore, we can say that this thing. Therefore, we can say Fn is equal to omega of Gn, which represents the lower bound, which is equal to omega of n cube, because our Gn is n cube. Right? I hope you are getting this, where we are going with the lower bound. It is as simple and as same as the upper bound. We are just using a notation, a symbol to represent that lower bound, because we have created a complex polynomial from our algorithm, and we cannot peg or we cannot associate a complexity class to it, known complexity class. So we will tell that this has a lower bound of this. So that is what this particular thing tries to call out. Now next, let's try to get into a deep dive of omega. And what we'll try to do is, we will try to align this particular number line, if I so call it, in terms of the ascending order of time complexities, to prove that, just like we proved for big O, that if we find the upper bound, anything to the right of that upper bound in terms of the conventional time complexities also become the upper bound. Similarly, for big omega, what we are trying to prove is, what we are trying to prove for the lower bound is that if we prove that omega has a value of lower bound as whatever that value is, then anything to the left of this particular omega value, right here, anything to the left of this particular omega value, wherever we find this, anything to the left of this particular omega value will have a lower bound which is valid. So if we find that n is a lower bound, anything to the left is a valid lower bound. That's what we will try to prove now. So if we actually see this, right, it's a no-brainer that we will need to prove in this manner, right? We will have to be careful that now we are talking about c dot gn to be lower, that is Fn will be higher. So we have to have the greater than equal to here, right? So if we have that, then what are we trying to show here? We are trying to say that Fn is equal to 5n plus 5 and Cgn is equal to 5n. So what we are trying to show, we are saying that n equal to 1, c equal to 5. If n equal to 1 and c equal to 5, then this becomes 10 and this becomes 5. So immediately this becomes greater. So even if I check the rest of the cases, n equal to 2, n equal to 2, c equal to 5, right? If I put n equal to 2, it will become 15. 5n will be 5 2s are 10, so 15 is greater than 10. If I put n equal to 3, then this becomes 20 and this becomes 15. So this is still greater. So we have actually satisfied this at n equal to 1 itself. That is, here we can say that at n equal to n0 is greater than equal to 1, we have this satisfaction that the CGN will be lower than this Fn. And when we say that it is lower, then we have satisfied this. Because we have satisfied this, we can now say this. That is, we can say our Fn is equal to big omega, that is a lower bound of Gn, right? And I know that my Gn is what? My Gn is n. Cgn was 5n, which means Gn is n. So now you have got n as your lower bound. So anything to the left of n is also your lower bound. Can we check that? Let us check that. Let us check that. So we will take another function fn, the same polynomial 5n plus 5, and we will try to see if there exists a Gn which is to the left of this n, because last example we proved n is the lower bound. So we will try to see if we can get something like root over n, log n, 1, etc. on the left side of the omega. So we will see that our Cgn is actually equal to 13 root over of n. Now this 13 root over of n will need to be substituted with n equal to 4. So if we put n equal to 4, 5 4s are 20, 25 is what we get here. And be careful, we have to prove that this is greater than equal to. Right? So what we are saying, 25 Cgn 13 root n. So what we will come to at is that n is equal to 4. Root over of 4 is 2, 13 2s are 26. So this is not greater than 26. If we put n equal to 9, then 5 9s are 45 plus 5 is 50. And we have 13 root n, n is 9, 3, 13 3s are. Okay, so we have, 13 root n is 3. So 3 3s are 9, 3 1s are 3, so this is 39. So we have 50 greater than 39. Which means we have satisfied this equation. So if we have satisfied this equation, then we have the liberty to call this out. And where is our inflection point? Inflection point is somewhere in between these two. So we can safely say that at n0 greater than equal to 9, something will happen in terms of this curve staying below fn. So this curve will therefore become my omega curve, or this curve is my lower bound. Right? So that's where we will say that this is how we have defined omega, and we have the liberty now to put this. So we will say fn is equal to omega of gn. And what is our gn? Our gn is root over of n. So fn is equal to omega of root over of n. Hence we have proved that while the same function had a lower bound of root over n, it also has a lower bound of, the same function had a lower bound of n, it also has a lower bound of root over of n. Right? So it might have had n like this. So that was your C2gn probably. That is some constant 5 into n. So this is also a lower bound. 13 root n is also a lower bound. In fact, it would be below the lower bound of this function. So I don't have space to draw. I had to draw it here in between this, right, as the lower bound. That is the n, this n particular class, right? It is also the lower bound of this function. It is below this class. So the previous curve, this line is what I am talking about, this particular line, right? This particular line will be somewhere here. And below that, there will be a further lower bound, which is 13 root n. Below that, there will be a further lower bound, which will be your log n. Below that, there will be a further lower bound, which will be your 1. I hope you are getting this point. So that's on big omega. Now that you know that for a complex polynomial, which you cannot represent in terms of time complexity, in terms of the conventional complexity classes of time complexity, you would rely on the upper bound and lower bound provided to you by big omega and big theta. Sorry, big omega and big O. We are now talking about theta. Now what is theta? Theta is a tilde bound. Now theta says that can you give me a common gn? See, can you give me a common gn? Can you give me a common gn with two constants c1 and c2 such that one of this will be below fn, one of this will be above fn. That means this definitely will be the upper bound and this definitely will be the lower bound. If that happens and you have a common GN, then that GN becomes your average bound. Not average case. I will never say case, best case, worst case, average case. I will never say that, because the lines represent that. We are trying to create two more lines above and below, and the third line is the average bound, not the average case. So that's what we are trying to do now. I hope you understood what we have here. So we have to prove that there will be a common GN, and that GN we can actually take. Now just see this. What is happening here? 5n plus 5. 5n. Let's take n equal to 1. If we take n equal to 1, 5n plus 5 is 10. And this also becomes, 5n plus 5 is 10. And this 5n becomes as 5. So what have we achieved? Can we say, because this is omega, can we say that CGN is below our Fn? We are trying to see omega, right? CGN has to be below. We are talking lower bound. So CGN is below, yes. CGN is below. So we have proved what? We have proved that Fn is greater than C1, or let's say it is, let's say C1 of Gn. Fn is greater than C1 of Gn. What is C1 here? C1 is 5. What is Gn here? Gn is n. What is Fn here? Fn is 5n plus 5. That is what we have proved. For this, if I take n equal to 1, then I have 10 as Fn, and I have 10 into 1, 10, and we have this as equal. So if we have this as equal, can I say that we have an upper bound? Because we can now say that Fn is less than equal to, because it is equal to, I can say less than equal to of CGN, right? So we are trying to prove big O. Big O means the upper bound. Upper bound means CGN should be upper than Fn, or CGN could be equal to Fn also. In this case, CGN is becoming equal to Fn. So it represents the upper bound. So what is Fn? Fn is 5n plus 5. What is CGN? CGN is 10.n. In that, our 10 is our, this is basically our C, and this is basically our N. So can we combine this both and say, in fact, let us call this as, C2 Gn, right? So C2 is equal to 10, C1 is equal to 5, Gn is equal to n, Gn is equal to n. So do we have a common Gn? Of course we have a common Gn. If we have a common Gn, then can I combine these two and say, because this was greater, this was less than equal to, right? Can I say that my C1 Gn, what is C1 Gn? C1 Gn is 5n. So my 5n is less than equal to Fn. Yes, I can say that 5n is less than equal to Fn. This is Fn, right? This is Fn. And that same Fn is less than equal to the 10.n. So 10.n. So this we know is C1. This we know is Gn. So less than equal to Fn, less than equal to C2, less than equal to Gn. Now this equation is the same as this equation. If that satisfies, I can say Fn equal to theta of Gn. That is the tight bound or average bound of Gn, which is equal to theta of n. So in this case, you have found that omega, in this phase, you have found omega for the function Fn, the omega representation is omega of n. The big O representation for this function is big O of n, and the theta representation is theta of n. So what did we find? We found that all the three are actually equal for this function. And that's what I was trying to tell you. If you notice here, you will see that we found that this was our big O, this became our omega, and this also became our theta, right? So anything above this is the upper bound, anything below this is the lower bound, and since both of them have n, therefore theta automatically becomes n, because theta becomes gn, where gn is common here, gn is common here, right? I hope you can understand this fact, right? So that's how we calculate our theta. Now, if we go and try to draw this, whatever we calculated, and this should be theta, right? I don't know, the previous slide also it was wrong, it was right, it was a typo here. So what we have is, from the previous slide we had Fn is equal to 5n plus 5, and we had calculated 5n as the C1, and we had 10n as our omega, right? So that's what we had calculated from the previous slide. So what we have, or what we can see now, is that so the big O was 10n, right? The big O was 10n, or for the big O rather, CGN was 10n, and for the omega, CGN was 5n, right? So see, here we have 5n, so of course this is the lower bound to this function, so this is representing your omega, and this is above this function, right? This function, and hence it represents your big O, right? So what we have here is, I think this is also a typo, my bad, I'm sorry for that. So this should have been actually not this way, this should have been omega here, and this should have been big O. So read it with that pinch of salt, please. Again, my apologies. Yeah, so now what we have is, we have calculated this from the previous slides as this, and all I'm doing is I'm representing this in the graph, and you can see that for a particular value of n, right, at this point you will get someone above this line and someone below this line always. Someone above the line and someone below this line always at this point, and hence this is your inflection point. And when I get someone above me and someone below me, both are actually complexity class of linear. Both are having complexity class of linear. So this is also big O of n. This is also big O of n. You can call it omega of n also, right? So all of them are the same, omega of n. And what we are seeing, because we have a common gn, right? We have a common gn here, that is our C1 dot gn is less than equal to Fn is less than equal to C2 dot gn, is what we are seeing from here getting satisfied. Fn is above C1 gn, Fn is above C1 gn, Fn is below C2 gn, Fn is below C2 gn, and we have a common function gn, right? And therefore we can say that Fn is equal to theta of gn, that common function, and that is equal to theta of n. So can we say that in this case our Fn has an upper bound of n, and Fn has a lower bound of n, and an Fn has what we calculated just now, theta, that is the average or tight bound of n. So all the complexities of upper bound, lower bound and tight bound are the same, and it's quite natural, because what was Fn? Fn, actually we said that let's complicate facts and assume that Fn is a complex polynomial. That's to explain you things. But if you see Fn, actually it's not complex, right? It's a linear complexity class. So you already had a polynomial which was following a linear complexity class, and then you said give me the upper bound, lower bound. As I said, if you have something which is following a complexity class, then the upper bound will also be that complexity class, the lower bound will also be the complexity class, and therefore the tight bound will also be the complexity class, because it follows Gn, right? And that's what we have just now established, that theta is basically going to be aligned with this Gn, provided you can find out a common Gn. with different constants C1 and C2, so that ultimately you satisfy this equation. And if you can, then you can actually call theta as Fn as theta of Gn, and therefore in this case it became theta of n. So I hope that makes theta understandable. And if you just imagine that there will be an upper bound, there will be a lower bound, and theta is basically in between, trying to represent the average case or average bound of the function, then you will understand that the essence of theta, right? And of course, the essence of theta can only be appreciated when you have a complex function. So as I was saying in the beginning of this lecture, we had started off with a complex function, which was this, right? This was the complex function with which we started. And we are saying that that complex function will have a theta, or can have a theta, which will be defined by whatever way we assigned the functions to the constants of C1 and C2, right? So we have to satisfy this for that to find out what is the Gn that can be applied to that particular function. So that's how you calculate theta, or that's the concept of theta. And I hope you can now understand and appreciate what we are trying to establish, right? So one last thing is, you had calculated n as your order of n. So anything to the right is the upper bound. You had calculated n as the omega of n. Anything to the left is your lower bound. Because n is the same, therefore you are free to calculate theta as n itself, because this is common to both the upper bound and to the lower bound. And therefore, because it is common, it becomes your Gn, right? And that's what this definition actually says. So that's how you calculate it. I've explained both the application and the calculation part of omega, theta, and big O. I hope it makes sense. And I think it will make more sense when we do some of the common university questions that are asked. So if I just take a small break now, with your permission, we'll be coming back and we will start solving common university questions that typically comes, so that your knowledge about this is perfectly clear. Let's meet on the other side of this break. Welcome back. Let's start off with what we left before the break, which is solving the common questions that typically come. Let's start with this, which says find big O and omega given a polynomial. So I already explained in my previous block before the break that if you are given a polynomial, then you'll have to apply the formula to actually calculate big O and omega. If you are given an algorithm, then probably big O and omega, they want to say worst case and best case. So then you'll have to probably see the algorithm to actually figure out what is the best case, what is the worst case. So here they are talking about omega and big O, which means they are talking about the upper bound and lower bound. But if they would have given you an algorithm, then they might want to see the best case and worst case, what omega and big O would actually represent. So you have to be a bit careful. As I said, some people treat omega and big O as the best case, worst case. So if such a question comes, you'll always have to take it with a pinch of salt, right? Now, what we have now is a polynomial. If you have a polynomial, apply the formula they are asking for, upper bound, lower bound. If you don't have a polynomial, if you have an algorithm, assume that they are asking for the best case, worst case, average case, right? So let's move on. Let's see what this would come to. Now let's calculate big O first. So we will calculate big O on this side, we will calculate omega on this side, and then we'll compare. So the way to calculate big O, I've already told you, right? If you have a function fn, which is represented as 5n square plus 2n plus 3, then on the right side, please put everything as 5n square, 2n square, the highest degree, plus 3n square, right? And then you actually get on the right side 5 plus 2 7 plus 3 10n square, and on the left side you have 5n square plus 2n plus 3. Now you will have to prove this. You will have to prove for big O that your function is less than equal to the CGN. So this is your CGN, right? And you are trying to calculate something above your function. So the function has to be less than your CGN. This function has to be less than or equal to your CGN. So that's what we have to prove. And hence we will say now with n equal to 1, this becomes 5 plus 2 plus 3, which is 7 plus 3 equal to 10. And on the right side, we will also get 10. So we have equal to. So have we proved Fn is less than equal to CGN? We have, right? We have proved that because 5n square plus 2n plus 3 is less than equal to 10n square for n greater than equal to 1. We have proved that. And that's the proof for satisfying big O, as you would have seen in the previous part of this lecture. Hence, we can say our Fn is big O of n square. Why? Because Fn is actually, if I break this down one more step, then Fn is big O of Gn, and our Gn is n square, right? So our Gn is n square because of this. So we will say big O of n square. So that's the answer to this. Now that same polynomial, if I take Fn as 5n square plus 2n plus 3, and this polynomial on the right, I want to express omega, I want to represent a lower bound, then let us remove all the powers which are not the degree, right? And therefore on my right hand side, let us just keep 5n square. So then can we say that on the left hand side we have 5n square plus 2n plus 3, on the right hand side we have 5n square, and let us take n equal to 1 and see what happens. So this becomes 10 again, and this becomes 5. So is 10 greater than 5? Of course it is, right? And we wanted to prove that only. We wanted to prove that this Fn will be greater than equal to this. That means this is running below Fn. Fn is above. And that's what this is proving. So what have we proved? We have therefore proved that our Fn is greater than equal to C dot Gn, right? Because we have proved 5n square plus 2n plus 3 is greater than 5n square for n greater than equal to 1. So if we have done that, that satisfies our omega equation. Therefore we can say Fn is equal to omega of Gn, and in our case, what is our Gn? Our Gn is this. So this is our C, this is our C, and this is our Gn. So this is our Gn, right? So this means that our omega Gn will become omega of n square, right? So what are we saying? We are saying that this particular Fn, again the same concept is arriving, this particular Fn is a known complexity class. It's a known complexity class, right, which is n square. And we have asked, give me the upper bound of this, give me the lower bound of this. It will be n square, na? All these will be n square because it's a known complexity class. The upper bound, lower bound will coincide with the main function, and hence because n square is the upper bound, n square is the lower bound, therefore this also becomes theta n square as the tight bound. So Fn is also equal to theta n square, right? Because your n square, which is Gn, is the same for your lower bound and your upper bound. And if that's such a thing happens, then your theta will also be n square. So for any conventional complexity class polynomial, your theta, your omega, your big O will all be the same. Now let's move on to the next problem. The running time complexity of a linear time algorithm. So linear means that you would have a loop, and that loop will go around certain elements, let's say arrays, right? So you have these arrays, and every array element will be checked, right? The running time complexity for a linear time algorithm will be the worst case scenario, because all the time your algorithms, if they don't say provide the best case or the worst case or the average case, you'll always go for the worst case, right? The worst case of the polynomial that runs through an array. So if you have an array like this, right, the worst case is what? The worst case is that we will actually get to see the element we want to search at the end of the array. That means we have to go here, search it, no, it's not found. We have to go here, search it, not found, not found, not found, and finally we reach here. And that represents our worst case of the algorithm, which is equal to n times that we had to go through, right? So n times we had to go through in order to find an element which is at the last pocket of the array. And that's the worst case of that. So the running time complexity of a linear time algorithm, they have not provided a polynomial. They have said a linear time algorithm. So assume a linear search. So in a linear search, you will be going like this, iterative manner. So it's an algorithm. As I said, for any algorithm, if they want the time complexity, it has to be the worst case time complexity, or they might say, give me the best case, average case, or worst case time complexities. Or they might even say, give me omega, give me theta for this particular algorithm. In that case, omega theta will be unfortunately need to be tied to the best case, average case, etc. Because that's how the world looks at it. Some portion of the world looks at it rather. So the running time complexity of a linear time algorithm is actually n, right? So you can represent it as big O of n, right? So you can write it as omega of n. You can write it as theta of n. Why? Because this particular n is a known complexity class. It's a known complexity class, right? If this, which is what? Y equal to mx plus c. This is a known complexity class, which is linear class, right? So this is a linear class. If it's a linear class, your tight bound, upper bound, and your lower bound will all be the same. So it can be omega of big O of n, omega of n, theta of n. You can write anything should be true. But as I said, it is always preferred that they will tie worst case with big O, and because you are supposed to find the worst case here, write it in the format of big O. Now, define asymptotic notation and explain each types. I have done that in this lecture. Please refer to the previous slides. And of course, you have a download link to actually download the slides, which will have a note section from where you can actually get the theoretical portion that you can write for your examinations. What is the search complexity in direct addressing? Okay, so this question means that if you have something like an array, again, and in this array, if we are trying to address the elements by their index, what is the time complexity? That means direct addressing of this array. So if we want to actually find out, or rather access the element, which is at index location 0, then we will say ARR 0. If we want to access the array which is at location 1, we will say 1. ARR 4 will access the address the element at the location 4. So this will be actually 8. This will be actually 10. This will be actually 7. So what is the time taken to address or time taken to access it using this method? Using this method, what will happen? Right? What is the search complexity when you are trying to search an element by its index? Right? What we are saying that at the fourth index, does the element 8 exist? Or does the element 9 exist? So what it will do? It will directly hit the fourth element and it will check whether the element exists. What time is required here? Let's say the time required is t1. Right? So let's say the time required to try to access this fourth element is t1. Now, similarly, if you search for 7, then you might have searched at the first index, is my 7 there? So let's say the time taken to access that is t2. Don't you think t1 will be equal to t2? The time taken to address a pocket, any pocket for that matter, is constant. Time taken to address a pocket of an array using direct index addressing is always constant, because it directly hits that portion of the memory and gets the value from that portion of the memory. Right? So irrespective of which portion you ask it to go, it will always take the same amount of time. Therefore, it is constant time. So if it is constant time, then the Tn will be represented as big O of 1. right? So that's what you will write as an answer to this question. Which notation comprises a set of all functions hn that are greater than or equal to cgn? Now this is the classical example where it says that my hn should be greater than or equal to c dot gn, right? For all n greater than or equal to n0. Now, what does this mean? It means your function is above c dot gn. That means c dot gn is the lower bound. So this actual statement tries to find out the lower bound, which is omega, and therefore which notation is actually omega? The answer to this question is therefore omega. I hope you understand. Next, we have this, which is basically talking about removing the recursiveness of this function and putting it as an expression which is not going to be having a function clause associated to it. So we'll have to remove this and see what the expression comes. So that's the that's what this particular problem is demanding of you. So how typically we do it is that if we actually see this, then fn is equal to this, which is fine. So if I put f instead of n, if I put n minus 1, let's say n has become n minus 1, then instead of this n, I will put, so I'm taking f, I'm substituting n minus 1 here in this n, right? Therefore, my left hand side becomes fn minus 1. On my right hand side, for each value of n, I'll have to substitute n minus 1, right? So I'll have to substitute n minus 1 means n minus 1 minus 1, which is n minus 2, plus this n also has to be substituted with n minus 1. So I can write fn minus, from this equation I can write fn minus 1 as this. So if I mark this equation as 2 and I mark this as 1 and 2, then if I say putting 2 in 1, right? Why? Because in 1 I have fn is equal to, check this, I have fn is equal to fn minus 1, and fn minus 1 I've already found. So can I substitute fn minus 1 here? So I will say this fn minus 1 is fn minus 2 plus 1 by n minus 1, and that is my fn minus 1 plus 1 by n, whatever is left here. So plus 1 by n. So I substituted this and then I added this 1 by n, right? So this becomes my fn. Now can I put in this equation, can I put fn minus 3, right? So sorry, fn minus 2. So if I put fn minus 2, then what will happen to this equation? So this equation will become, we'll put fn minus 2 here in this equation and see what it happens, right? So fn minus 2, which means this will become fn minus 3, and we'll have n minus 2 put here, so 1 by n minus 2. Can I mark this as 3 and can I mark this as 4? And then I say that putting 3 in 4. So what I will do, I will take this fn minus 2 and put it here, right? So now what we'll do is we'll say fn is equal to fn minus 2 is actually fn minus 3 plus 1 by n minus 2 plus we have this 1 by n minus 1 plus we have this 1 by n. That is what it is coming to. So if you can see now that this is going on, this goes on, and we'll have to take an arbitrary integer where this is an intermediate step. So if I take a jth iteration, so we did till third iteration. So if we take the jth iteration, then fn will be equal to fn minus j plus 1 by plus 1 by n minus j plus 1 plus 1 by n minus j plus 2 plus dot 1 by n. right? Because this j could be any iteration beyond. This is the third iteration. So after the fourth iteration, there will be something. Fifth iteration, there will be something. Jth iteration, it will look like this. What I did, I just said that my n minus 3 is n minus j, because I am at the jth iteration. So if n minus 3 is n minus j, then n minus 2 should be n minus j plus 1. And n minus 1 should be n minus j plus 2. Right? So this is what fn minus j will come to. Now, in such problems, you would have two conditions. One, this condition which talks about the recursive condition, and one, a base case condition. So this is your base case, that f1 is equal to 1 for n equal to 1. So this fn, f1 equal to 1 is your clue, that if I can make this as f1, then I can put 1 here. How can I make this as f1? If I say that n minus j is equal to 1, then this becomes f1. So if n minus j is equal to 1, then what is my j? My j is n minus 1. Right? So can I therefore say that my fn is equal to f1 plus my j has become n minus 1. So don't you think that this will be 1 by 2? Because my n minus j is 1, or you can treat it as j equal to n minus 1. Either ways, solve it, you'll get 1 by 2. Solve the next, you'll get 1 by 3. And in this way, it will go on till 1 by n. Now, if you put f1 as 1 or 1 by 1, because f1 is already given as 1, you will get 1 by 2 plus 1 by 3 plus 1 by n. And this is nothing but a summation of k equal to 1 over n of 1 by k, right? So that is basically a harmonic function that we are actually arriving at, where we have eliminated this recursive call, and it has come to be something which we can now calculate without recursion. So summation of k over 1 to n of 1 by k is basically the answer to this question. So that brings me to the end of this particular lecture on asymptotic notations and the discussions of the previous year questions on asymptotic notations. I hope I've been able to substantiate and tell you that the big omega, the big O, and the big theta are not best case, worst case, and average case complexities as some of the people would think like. They are more to do with finding out the upper bound, lower bound, and tight bound. That's it. And I am sure you can rewind and understand those portions where I have explained why. I'm sure you can understand how to calculate big O, how to calculate omega, and how to calculate theta, and the problems associated with it. So we'll meet in the next lecture, which would be around the linear and binary search. Till that time, have a nice time. Thank you so much.